It's a pleasure today to have our Colloquium Benedetto Piccoli, who's one of our members and faculty at Rutgers. I typically, when I'm booking flights and I typically see the price, which is too much, I curse several of our colleagues for being responsible of this optimization on the side of the airlines. But, here's a guy who's actually trying to do something good for society, which means lowering the amount of time that we are stuck in traffic. So please, Benedetto, tell us how you're going to pull this off.
Thank you very much. So first of all, thanks for having me. It's a great pleasure to give this talk. And as Camillo said, we try to optimize, but it's not, I'm not sure we succeed. So it's an attempt. So this picture is from an experiment involving autonomous vehicles we performed in November 2022. And I will come back to this towards the end of my talk. So, but let me start doing a little bit of history of traffic modeling and its relation to data and mathematics. I'm sure some of you may be not that familiar with this history, so I will tell you a few things. But let me start indeed with a little clip. This is what we call stop-and-go waves. So this is in Atlanta, a camera that is picking traffic, and you see people start to slow down, and that this slowdown travel backward in traffic. And indeed, multiple slowdown may happen, and then travel backward in traffic for miles and miles or hours. Okay, well, maybe not hours, but several minutes. So I want to start with this to point out two things. One, because it was one of the main phenomena of traffic that we were trying to address. And the second one, to say, traffic is a very complex phenomenon. So let's see why it's a complex phenomenon. Well, let's think about what is traffic. Well, there are multiple components in traffic: the infrastructure, the roads, the traffic lights, the overhead signals, and so on and so forth. There is the agent dynamics. So when we talk about agent in nature, in this case, we mean the cars. And then there are the internal dynamics of agents. So the infrastructure, I don't know if you ever see, but these are two pictures of infrastructure that are built by humans. We don't tend to do simple things. This is a double roundabout in UK, and this is a true traffic light. I don't remember where. So, we complicate things a lot. And we can describe the system at this level, sometimes called mesoscopic or microscopic. That is, you try to look from far away and understand what the system does. In that sense, it behaves a little bit like a fluid to some extent. There is a flow going on these roads, and it changes in direction and so on and so forth. But it's also very hybrid. Hybrid in the sense that there is continuously discrete and variable that enter into the game. For sure, traffic lights, right? We have to stop and then restart and then restop. So there is a lot of complications. And also, this infrastructure is partly continuous, partly discrete. You need to make these maneuvers of changing lane, of turning, and so on and so forth. At the level of the agent dynamics, it's also very complicated. I mean, there is a long history of the automotive engineering. And nowadays, all engines are essentially highly electronic. And usually you have hundreds of variables to describe how an engine is working. And similarly for the aerodynamics. So you see PDE and large system here appear as well. And this is just the dynamic of a single engine. Not only that, but continuing on the parallel with the gas dynamics, cars are very different, even in the basic physical principles, because they can continuously inject or take out energy from the system. We have gas, if we didn't forget to put gas in our car, and then we can accelerate that, inserting energy in the system. Not only that, but there is the internal dynamics. Sometimes we may talk about the nanoscales. So within the agent, there is a human. The human is very complicated. Even the process of driving is a cognitive process, is very complex. And obviously, there is also a behavioral part. I mean, Camilla and myself, we are Italian, so we know that, there is a lot of behavior also going on traffic. And this is really a nanoscale level, and mixing with the cognitive process, psychology, behavior, and so on and so forth. So let me do a little bit of a mini history of traffic modeling and where the modeling intersected with mathematics. So back in the 30s, it started here in the United States. These are pictures of green shield measuring the traffic exiting the Lincoln Tunnel in New York. Okay, so he was taking pictures of how many cars were there, multiple pictures to determine the speed of these cars. And then he was able to use a basic physical principle like the flow is the density times the speed. And this is a constitutive law that is valid not only for traffic, but for gas, for fluid, for whatever. And then measuring things. He was taking measuring like this. As the car density increases, the speed typically decreases. This is very understandable, right? When there is a small number of cars, you tend to go to a higher speed. When there are a lot of cars, you slow down and you may go to zero when cars are bumper to bumper. This means that if you look at this flow versus density, this is the typical shape that you see, like an inverted bell. You start with zero flow if there are no cars, you reach a maximum flow, and here usually you call this part free flow. And then it started the flow to deteriorate. Okay, the speed goes down and the flow deteriorates until it goes to zero when you are bumper to bumper. You simply don't move. So if you assume that we jump from the 30s to the 50s, late 50s, people started to use indeed conservation laws. They started to assume here the speed is indeed function of the density. You see here we are measuring, we assume it's just function of the density. Then we can write just a conservation law. This is a partial differential equation expressing the conservation of number of cars. Rho is the density, T is the partial derivative with respect to time, V is the speed that depends on density. This product V rho is the flow, and this is the partial derivative with respect to space. Okay, so it's a single conservation law that expresses just the number of cars is conserved. That is most of the time true. So conservation laws, even a single conservation law like this PD is a bit complicated. What does it mean? For instance, you may start with very smooth initial conditions, even analytical, and they would develop in finite time discontinuities. Well, obviously, this means that you may have a multi-valued solution, then you introduce solutions in weak sense, and solution weak sense develop discontinuities. These discontinuities are called shocks, and usually they travel in time. Like the stop and go waves, they travel in time many times backward, okay, with respect to the direction of traffic. So stop and go waves are a complicated phenomenon, but just a queue at a traffic light may be represented by a simple shock. Okay, so there are cars stopped at the light, and then other cars arriving, and you notice a discontinuity at the end of the tail. So there is a high density, a low density, cars arrives and accumulates. This discontinuity travel backward, and this is well explained by a shock. If you're a bit familiar with gas dynamics or conservation laws, then usually you don't have unique solutions. So you introduce physical concepts like entropy to select a solution. And in particular, there is this famous Rankine-Gonio condition that essentially tells you what is the correct speed of a shock, okay, to be entropic, so to be physically relevant. I specifically mentioned this because in next slide, we will talk exactly on how to use this relation in real traffic. So we are now jump ahead of around 50 years. This is in 2008. I was living back in Rome, and in Rome you have a big belt, highway belt like you have in DC, okay? And we were gathering data with this device called clear boxes. So the game is the following. If you want a discount on your insurance, you're gonna mount this on your car. This is monitoring your driving style. And you know, the insurance then will decide what to do with that information. So we talked to the insurance company and they were giving us the data, obviously anonymized. We don't know who is that. But this is a piece of the highway belt around Rome. This is the space. So we are focusing on 18 kilometers between these 2 points. This is a space, this is time. And you see every single dot here is a measurement from one of these devices. So it's sending a measurement that identifies, okay, there is a vehicle in that position at that time, and the dot represents the speed. A bigger and lighter in color dot means higher speed, and smaller and darker dot means lower speed. So immediately you see here is free flow. People are going fast. This is a congestion. You see this very small dot means that these guys are almost stopped. Okay, they are like about almost bumper to bumper. So here there is a big on-ramp, and you see this starts at 6 in the morning. So there are some traffic forming here because of more ramps. More people are jumping somewhere here on this highway, and then creates all these dynamics of queues and so on and so forth. And you see, if you see, there is a clear identification you can do from data of a kind of queue that forms and travel backward. And then much later on, when the density decreases, there is another discontinuity traveling the opposite time. Well, you can compute exactly the speed of these two discontinuities that are both shocks in terms of this Rankine-Bonnier condition that tells you that the speed at which this shock travels is given by the jump in the flow along this continuity divided by the jump over in the density. Okay, so you see here, beautiful math explain immediately phenomena that are well observed with data. And it's interesting to notice that sometimes people were giving just this data to data crunching software, like, but nowadays it would be AI. Now it was 16 years ago, it was, first generation AI, and they were not making a sense of anything. But beautiful, simple math immediately explains what's happening here. There is a shock traveling backward, and then when the density goes down, this shock becomes with high speed and indeed travels backward and solves the congestion. So I hope I convinced you that there is a very long history, more than 70 years, more than 80 years of interaction between traffic, data, and mathematics. So let me now add another element to that, or maybe, sorry, let me go backward just a second. You see, the backward button is useful. So let me add one thing. Here you see that there is a dark, lighter color, dark, lighter color, dark. This is your typical stop and go. So if you would be a car that traveled there, you would arrive, stop, then reaccelerate, then kind of in the middle, then stop, and then reaccelerate, and so on. So you can indeed see even in data this type of phenomenon. So speaking again about the stop and go traffic, let me introduce a new element here. So we talked about math, we talked about data, math modeling data, but another element are experiments. So traffic, there are the real traffic, and you can conduct experiment. Experiment can be done in open sense. You go there, observe traffic, and try to influence, or in a restricted environment. This was a very seminal experiment that did also in the mid of the 2000s that asked, is it true that stop and go waves are so common? Or it's just that people think to be in a stop and go wave, but there are not so many. So they used a restrict setting. It was called the Tsujiyama experiment. A restrict setting means that they organized a ring road and they put cars that would start at the same distance and would reach the same speed, and they would let it go. After a while, there was no instruction given to the drivers except try to drive at your speed and be safe. Don't crash the car in front. After a little while, with no instructions and with no apparent reason, you see a stop and go waves form. Here, cars start to be stopped, and then they reaccelerate, and the point where they stop travels backward. So it's very similar to the stop and go waves that we observe in real traffic. And you see, it resembles a lot to what are the shock characteristics. There is a big discontinuity, for instance, in speed, and this discontinuity travels backward with respect to the flow. So this famous experiment essentially told us a couple of things. One thing is that you don't need a particular reason for this wave to raise up. What I mean is, well, some waves are generated by the network. There is a merge, there is an on-ramp, an off-ramp, and it's obvious that creates some dynamics there. But these are not created by any of those features. They happen essentially either because of some events, like someone gets distracted, nowadays with mobile phones, it's very common, and then suddenly breaks, right? Because, oh, where am I? And breaks, and then creates a discontinuity. Or even simply because we are all different, so our reaction times, our attitude towards accelerating and braking are different, and these differences render the uniform flow an unstable equilibrium. And so whenever there is a small perturbation, then we jump towards a much more stable equilibrium that is the traveling wave. Well, equilibrium in the sense of dynamic equilibrium. So I want to then organize this talk essentially in three little parts. In the first part, I will tell you what is the math behind using the data like the one I showed from Rome, okay, and what were the success in that area. So the area of traffic monitoring using math. Then I will pass to say, okay, now let's go to the next stage and let's try to control traffic. And specifically, let's focus on stop and go waste. And I will talk first about the math involved into that, and then about the big experiment that I showed the picture from at the very first slide. So first of all, if you want to deal with traffic, and even if you start with a very simple model, the likelihood with unreacher, the single conservation law, the first difficulty you encounter is that traffic doesn't happen just on a stretch of road, but on a very complicated network. So indeed, you have a network of roads, highways, and so on, and you ask yourself, okay, if I put one equation there describing traffic like a single conservation law, just to be clear, people used also systems of conservation law, so more complicated dynamics, but let's start with just one conservation law. Well, it's interesting because here it could mean just a system if U is a vector. So, you know, I'm not making any assumption. And let's see what dynamics do we have to put in nodes to make sense both mathematically as a theory and the modeling to model the phenomenon. There are some obvious things we can think. We want our cars to be conserved through a junction. You know, we don't want cars to disappear there. So there should be, yeah, maybe, well, it's interesting because when you talk to engineers and you say conservation laws, they immediately start to object. Oh, there is a parking. Oh, there is someone, you know, having the car that broken up and, but okay, we understand each other, except some, you know, events, it makes sense to see that the number of cars is conserved at the junction. Okay, that the cars will come and from one incoming road, they possibly go into some outgoing, so at least the vast majority of them. So, but then there could be other you know, consideration to make. Let me point out for a second, I will come back to that, that we need to take into account also the math. Now, conservation laws, as I showed you already, develop this continuously finite time. So you need some functional analysis tool to deal with that. And it's even more complicated because being fully nonlinear, the classical functional analysis doesn't work that well. And you need to use really your hands, work with L1, BV spaces, and try to do theories that are not very simple. Here, there is a further level of complications because, you know, what is a node here? Well, it's essentially a place where three different conservation laws meet, right? And you can imagine that solving the dynamics means pairing these different conservation laws. But indeed, it's a boundary value problem because if you take a single road, it has this acts as a boundary. Now, because of the nonlinearity, when you solve boundary value problem to conservation laws, it may happen that solution does not attain the value at the boundary. So you prescribe a value at the boundary, and the reasonable physical solution does not attain that value. This is a complication from a modeling point of view that needs to be absolutely taken into account. Okay, so first observations. Well, first of all, conservation of nodes, if you impose conservation nodes, is very far from determining a unique dynamics of a network. So additional rules will be taken into account. I will show very soon what is reasonable for traffic. Solution gives rise to boundary value problem. These mathematically are complicated. It's reasonable to assume that you may use entropy as is done in gas dynamics, as is essentially underlying the likelihood with richer models as well. And there has been a lot of results starting, well, there was a single paper in 95 by Holden and Risebro, two Norwegian investigators. And then there was an explosion starting around 2005 of papers that started to deal with this theory. So there are more or less nowadays 20 years of history of this theory. And we wrote a large review in 2014, what was in Journal of the European Mathematical Society. And just between 2005 and 2014, we collected something like 120 references. So people were writing at least 10 or more papers on this subject per year, but more than that probably. So what is the result after those 10 years are, well, a pretty robust existence theory for linear assumption. Uniqueness continuous dependence has been achieved just in some special cases. I will touch upon that. And let me just say, that's okay, many other extensions that make sense for traffic. Like sometimes we call multi-commodity. It means essentially that you have many different type of vehicles that travel on the highway. Large buses, trucks, simple cars, large SUV, and so on and so forth. Some of them transport people, some of them transport freight, and so on and so forth. So from the engineeristic point of view, you can complicate things very much. And a lot of results happen at all level, modeling, numerics, control, optimization, and also the applications. So let me talk now about a basic fact of what you do usually with conservation laws. With conservation laws, you typically do the following. You want to construct a solution, say, to a Cauchy problem, and you approximate the initial datum with a piecewise constant function. Like you see on this interval, you have a constant function. And then you see along this discontinuity, an initial value problem with just one discontinuity is called the Riemann problem, because Riemann was the first one dealing with this problem. And this problem is very well understood, and solution can be constructed. For instance, let's assume we are in a simple case of a system with, say, just two equations. Then every solution will give rise to a couple of waves that are either shocks, so traveling discontinuities, most of the time backward with respect to traffic, or rarefactions. Rarefactions are continuous waves that start from a discontinuity and opens it. So discontinuity exists just at initial time, then it opens up and becomes not necessarily smooth, but at least a continuous curve. So a combination of these waves for every Riemann problem, if you piece them together, you define a weak solution. Well, this is a technical aspect. Sometimes it's convenient to approximate these continuum waves with many small discontinuities. It's technical, don't bother too much about that. Then what I'm explaining is really what is called the wavefront tracking. What happens is that you continue your solution until first two fronts interact with each other. Then at that point, you have a new Riemann problem with two data. In this case, would be the data that was here and there. And then you continue to solve that Riemann problem and so on and so forth. This method works very well, but there are essentially three things you need to be able to estimate. First of all, the number of waves. You see that here is the number of waves, for instance, in this case is increasing, right? I have two waves incoming, this plus more exiting. Then you have the number of interactions, because the more waves you have, the more interaction you're going to have. And then finally, the estimating the total variation. So as I told you, BV is the natural space for solutions. So you need to estimate B, the total variation, to have some compactness that pass into the limit. Here, those problems are very easily solved for one equation, are reasonable for two equations. Where there are more than three equations, two equations, like three equations on, you need to do, some complication like solving approximate some of this problem, introduce some non-physical waves, and so on and so forth. But let me go back to traffic. What is reasonable to assume that happens at a traffic junction from modeling point of view? So take this example. This is a bifurcation, and the incoming road is totally full of cars, and the outgoing roads are just empty. So what can happen? Well, maybe there is a very nice gelato place here. Everyone is turning right. Or maybe there are interesting things on both sides and they split, right? So it's very natural to assume, and that's what we do, that there is indeed a matrix that prescribes how people distribute to outgoing road from an incoming one. Alternatively, you say that the vector of outgoing fluxes is obtained by multiplying by a matrix, distribution matrix, the vector of incoming fluxes. Mathematically, yes, that's what you expect. There is a matrix alpha JI, J runs over outgoing road, I over incoming. There are numbers between 0 and 1. This means essentially the percentage of a traffic from node I that distribute on road J, and they obviously should sum up to 1, because as we said, we want conservation. So cars from road I should go to one of the exiting road J. So this is a stochastic matrix. But this is not enough to identify a solution to that problem, because you see, what may happen is the following. All right, no one has to pass, stop there. This is indeed, if you prescribe the solution to be constant in all the roads, this not only solves the conservation law, but solves also this relation. Because no one is going through, this is a 0, this is a 0, great. We solve that equation. So you needed to introduce more information, or more way of selecting a solution. And this is done sometimes by entropy type rules, like you maximize the L1 norm of the vector of incoming flux. So you want to model the fact that people want to go through the junction. They don't want just to stick there, because otherwise mathematically that's a perfect solution. Nothing happens. It's always the perfect solution, right? Nothing happens. A little bit more of dynamics at junction. Let me go a little bit quickly through that. It's a bit more technical, but essentially, because I told you that conservation laws do not, solutions may not attain the value of the boundary. What happens is that if you go back to that fundamental diagram, linking density to flow, and you assume that on an incoming road you have this density, you cannot generate any density on the incoming road. You can just stay at this density or go to this much higher density. And this happens if your initial datum, instead of being here to the left, called free flow, would be in congested flow. So the problem becomes nonlinear. So despite the fact that the traffic distribution matrix gives you a linear problem with the maximization, this problem is rendered nonlinear by those constraints coming from the conservation law. The rule A implies conservation of the junction, and A and B are indeed equivalent to a linear programming problem. But then deciding the density will be further complicated by this constraint you have on each road. Let's skip that, and let's just say that wavefront tracking is the method that is usually used for conservation laws. But when you do a network, there are further complications, because when a wave hits a junction, so hits a boundary, then there are much more complicated phenomena that will happen. But you know, we were able to develop a complete theory on networks. Again, you have a much more delicate problem in terms of increase of number of waves and also increasing the total variation. But essentially the strategy is that what is the natural quantity here is the flux variation. So you don't look at the total variation of density, you get total variation of flux. That's much more natural to control because it solves linear programming type problems at the junction. And then what you do, you estimate the number of so-called sonic waves that are shocks that cross that point of maximum in your fundamental diagram. Anyway, that's okay, maybe a little one more thing. If you want to deal with uniqueness, then the technique we used is Finsler metric on L1, built in this way. You know, naturally, if you have a piecewise constant function, there are natural vertical perturbation that would be the natural perturbation in L1. And we consider also perturbation of the jumps. If you look at perturbation of the jumps, this would define curves that do not admit a tangent vector in L1 sense, but admit a tangent vector in a generalized sense. This generalized tangent vector that perturb vertically and horizontally piecewise constant L1 functions, you can give a norm to that, and this defines a Finsler type metric. And if you prove that an appropriate norm like this one, you see the norm I'm giving here is that I'm giving the one norm to L1 perturbation, and then building up what is the measure of this move in the discontinuity is just the size of this movement times the size of the jump. So this is indeed, again, measuring how much you moved in L1. This type of tangent vectors, it's much easier to prove that these tangent vectors are contracting in length with respect to other technique. And this allows to prove you that these Finsler metric are indeed contracting. This ends the second part of the talk. Let me just conclude the story about monitoring traffic. Indeed, about monitoring traffic is a big success story because still in 2008, together with University of California, Berkeley, and other participants, and especially Nokia, a big experiment was performed called Mobile Sentry. So 100 cars were sent with phones on board. They were measuring position and speed. They were sending to a central system that in turn was sending back a signal saying, you know, green, there is no traffic, red, there is a low speed. That was the first experiment of traffic monitoring worldwide made with the mobile phones. And you know the history, in a couple of years, essentially the big industrial players picked up that. And in the last 15 years, all of us, we are using the phone, and the phone usually is typically using data of this type, mapping the traffic. And nowadays we have navigation with also traffic information that are really done with something like that. At that time was a true innovative experiment, but it was impressive to see that just in few years, from academic experiment, it went immediately all the way to industrial application. I can tell you even a little story here, funny one. You see here that there is a red. So the experiment ran for 1 day, from 9 a.m. to 5 p.m. The traffic on this I-8 in California was moved for the full day, except a certain point that, some red happened there. And the interesting point is that the team that was involved there, I was doing just the theoretical part, indeed was quicker than the highway service to detect the anomaly. Because obviously these data were flowing in real time, while the alarm service, our police report and so on. And you know what? There was an accident, obviously. And there are a lot of cameras on this highway. So they went to the cameras and they check. And obviously what happened? It was a guy using the phone that caused an accident. So, this was an experiment using the phone, and indeed, but it was not one of the cars involved in the experiment. It was just another person on the highway that caused the accident. So obviously phones can be very useful, but also very distracting. So my recommendation, don't use the phones when you drive. Anyway, the math beyond that experiment was, let me go quickly about that because this is more applied, but essentially you have your mathematical models, okay, conservation laws of network, then use numerical methods. There are a lot of numerical methods for conservation laws, from Wino to Godunov to, I will not even mention all that. But you have a continuous data inflow that comes from your cars. And so you need to do what is known as data reconciliation. That is nothing but a traditional filtering methods like ensemble Kalman filtering. And this was just essentially combining the three things: the mathematical theory of conservation laws of networks, the inflow of data that were coming from the phones, and some data assimilation algorithm that would combine the prediction made with the model with the inflow of data. I don't know if you are familiar with the history of Kalman filter, but essentially Kalman filter was designed for space application. And some people went all the way to say that the man went on the moon for two things: Newton's law and Kalman filter. I don't know if it is really true, but there is some truth to that. I mean, data assimilation and filtering are fundamental when you are dealing with the models combined with it. So this was the nice history of success in terms of data traffic monitoring that jumped into, industrialization almost overnight. Also because Nokia was involved in the experiment, and then obviously, they had the know-how to transfer immediately. Let me now pass to the more recent history and moving from monitoring to controlling. Okay, you can just observe traffic and you can try to influence it. I would try to be quick here because it's a lot of multi-scale math, but let me just put some comments here. First of all, essentially, if instead of looking at the macroscopic level, like conservation laws, to microscopic level, like a lot of agents, then there are many problems can be described by large agent system, ranging from biological application to crowd dynamics to population health that became obviously very famous with COVID. So if you do at agent level, there are billions of different applications, but let's see which type of math is involved in that. So the type of math that I think is most fascinating is this connecting the scales. Okay, you are at microscopic level. If you describe with 1 million agents, you have 1 million of these. From a theory point of view, you don't get much, right? We like to solve problems in 2, 3 dimensions, but if the dimension is 1 million, there is not much that we can say. So it's very natural to pass to the limit and go to another scale. A very natural limit is the so-called mean field. You see, let me write just a typical model of traffic. Position of a car, there is time derivative is the speed, and time derivative of the speed of the ith car is something that depends on the other cars. What is this mu n? This mu n is called empirical measure. So I define a measure that is the average of Dirac masses, center, and the position and speed of all the cars. This is a simple measure obtained as finite sum of Dirac deltas. It's normalized by the number of vehicles. Okay. This measure solves an equation that can be expressed in terms very natural in terms of the microscopic model. These are ODEs, ordinary differential equation. This is so-called Vlasov-Poisson equation. It's a partial differential equation. This is your measure mu. This is the speed. This is the gradient, and this is the other part, gradient with respect to d. So interesting enough, you take a solution of ODE, you just define the empirical measure, and this is automatically a solution to this Vlasov-Poisson equation. So what can we do? Can we do the same for a control problem? So now a problem in which the cars are not free, I mean, going free, but you control some of them. So whenever you try to do something like that, you hit the two main obstacles. One is like, okay, you insert a control here, but these mean field type limits work well when you have indistinguishability of particles. So the control should not depend on the specific agent. It should depend just on position and speed of the agent. So this limits a lot your possibility of exerting it in the mathematical framework to describe a control mechanism. The second part is that even if everything works well, you pass to the limit, controls, especially optimal controls, tend to be even discontinuous. So when you pass to the limit, you may end up with an additional term that is a measured term, and this measure may be singular with respect to your solution. So essentially in the limit, it's like if you wouldn't have any control. And this is a little bit like saying that you are controlling a big river with 1 billion toothpicks. I mean, you can have a lot of toothpicks, but most likely you're not going to do much in controlling a river. So let me go quickly through one of the ways we try to solve this problem. We split the population in two subpopulations. One population indicated with the small m is the vehicle that I control. For instance, some autonomous vehicles. And all the rest is the rest of traffic. Now, n is going to be much bigger than n. I will have probably a small number of autonomous vehicles and much more of the other vehicles. Then I'm passing to the limit. So you see, this is a representation. All the black ones are the one I don't control. The red one are the one I control. The YK, WK I control. This other one I cannot do anything. If you pass to the limit, then you keep m finite. You send n to the infinite. So this becomes a coupled ODE PD, Vlasov-Poisson PD. You see here the coupling comes through mu appearing here and mu m appearing there that represent the empirical measure of the ODE part. The interesting point is that you can define cost functional, for instance, minimizing fuel consumption. And you can pass to the limit in the sense that you can prove gamma convergence. So in particular, optimal control at one scale converges to optimal control at the other scales. And you can use this result in many ways, like studying theoretically this problem by finite dimensional approximation, or trying to design optimal control at this level and projecting down, and so on and so forth. Let me go very quick here. This is one idea of defining a new evolution for measures I defined a few years ago. So an ordinary differential equation, what is? Well, we may see as a section of the tangent bundle, so a map that to every point in a manifold associate a vector of the tangent bundle. The only requirement is that this vector should project down well. So you don't want to associate to X a vector that is not in the corresponding fiber. So you can generalize this map, for instance, if you immerse a manifold to the space of a probability measure of the same manifold. This map becomes a map from a Dirac mass center text to a Dirac mass center there. Why not define a general probability vector field as a map that maps probabilities on, for instance, Rn to probabilities on tangent bundle, require that it projects down well. So if you project down on the first component, you recover your measure. This is enough to define formally a measure differential equation that is an evolution equation for measures where solutions are intended in weak sense. So since mu is a measure, is by integration with the test function that you verify this equation. Time derivative is equal to what? Well, this d of mu is now a measure on the tangent bundle, and you integrate the gradient of your test function against v, where v is integrated in your v of mu that is a measure. Maybe I want to go to the more fun. Oh, it stopped. Yeah, but probably. Okay. I will just tell you before jumping to the traffic, tell you that there is a lot of interest in these equations for measures, and there are controlled equation, and there are many different approaches, some based on microscopic level, some interpreting traditionally as differential inclusion, some based on variational formulations, and various other generalizations. So the message here is that it is a very active research field beyond application to traffic. If you are curious about that, there is one recent paper looking at Lagrange-Eulerian and Kantorovich formulation. Kantorovich is in the sense of interpreting the solution as a measure over the space of continuous or more regular curves. It's called Kantorovich because it refers really to the Wasserstein or Rubinstein-Kantorovich distance, and it's find a nice interpretation. Or people try to use graph limits. These are new type of limits that are not Mayfield type based on what is called the graphon or limit of graphs. It became very popular with Laszlo Lovász and collaborators that used this framework in various applications. And so it's a very lively research field. There is a lot of research going there. But let's jump back to the more fun part. So let's go back to the traffic waves. So first of all, so what our attempt was, we want to solve traffic waves using autonomous vehicle. Well, obviously vehicles evolved a lot, right? The vehicles that were 100 years ago are very different from nowadays. Indeed, people see that even as an evolution, right, of human beings. And there are many levels of autonomy that are nowadays essentially postulated. Level 0 is like a car, with no level of autonomy. Level 1 is that automatic braking and this, something like that. Level 2 is like automated cruise control. So let me tell you what it is. Essentially, every car in the United States has cruise control. You go into the highway, you want to go at a given speed, you press cruise, set, and then your car will continue to keep that speed. I don't know, 60 miles per hour. I don't want to say miles per hour above the limit, right? So in Jersey, 60 miles per hour. And then the next evolution is the autonomous or automated one. What it consists of? They install a little radar in front of your car that measures the distance to the car ahead. Some upper level car do have this mechanism. Now you set still your 60 miles per hour, but now then what happens? This radar measures the distance with the car in front. So in case you have a car in front of you that is lower than 60 miles per hour, and this, this headway, the distance with the car in front is diminished, at a certain point the car starts to decelerate, okay, and goes to a lower speed. So essentially, if you have this mechanism, you don't have to bother. You sit 60 miles per hour and the car will do 60 miles per hour, unless there is a slower car in front that goes at a slower speed. It may go all the way to stop, if it's necessary, and then it will restart. That's called the automated cruise control. And this is considered a level 2 autonomy. That's exactly what we use in the experiment, okay? A level 2 autonomy. It's essentially a different version of automated cruise control. There are 3 other levels of autonomy, some of which start to appear in some upper level cars. There are some cars nowadays that they park by themselves, right? They have a lot of sensors that do that. So what we did is indeed just using level 2. Okay. So very diffuse technology. Again, this was still in Plana, this is in Dresden, and this was the consortium that we formed to address this problem. It has Berkeley, Rutgers-Camden, Temple, Arizona, Vanderbilt, government, Tennessee Department of Transportation, and 3 car producers, Toyota, GM, and Nissan. 70 plus researcher, 5 university, blah, blah, blah. A big stuff. Okay, we started indeed with trying to start from what the Japanese did. So the ring road, then we did platoon, and then we did the big experiment. Let me spend a couple of minutes on what we did on the same setting of the Japanese one. I will skip the platoon, and then I will jump all the way to what we did on the open highway. So let's see what we did in 2014 about it. So this was an NSF-funded project, and we started with the same setting as the Arizona, this is called the Arizona experiment because we did in Arizona, the same setting of the Japanese experiment. You see, we put cars in a ring, they start equidistant and the same speed, and there is one special car with a big arrow. That is our autonomous car. When the arrow is black, the car is human controlled, okay, with all the human drive. When the arrow will turn red, then the human is replaced by the automated system, okay? There was another person on board that would activate the automation and tell the human don't do anything anymore, and now he is driven by the computer. Okay, so see what happens. We started the experiment, and you will see graphically that after a little while, like it happened in the Japanese experiment, waves will pop up. You see there is acceleration and deceleration that happens. Okay, let me stop for a second to describe you what is here in the lower part. Here in the lower part in dark, black dark is the speed over time of the vehicle that when it's black is human driven and will turn red when it's driven by the computer. So you see, it started some oscillations, and then these oscillations becomes very clear waves, stop and go waves, accelerate, brake, accelerate, brake. All the other gray ones are the speed of all the other vehicles that were human driven, and they were not aware of what was going on. They were told to just, drive and be safe. So look what happens here. After the wave started and established, we turn on our autonomy. And the automated, the computer is driving differently. Okay, it sometimes leaves a little bit bigger gap, sometimes not. But you see what happens? Obviously, we designed the control on purpose. The oscillations are very much reduced. Indeed, when we target a 7.5 meters per second, we reach our best results. So our vehicle drives almost a constant speed, and all the other one oscillates much, much less, essentially destroying the wave. Right?
Well, that's then.
Sorry?
Well, now, you increase the speed.
Yes. So this was a not totally automatic control, in the sense that there were a couple of guys over the building observing that, and then we were communicating the guy that was in the vehicle with the human and telling them, okay, now tell the computer to target exactly this speed. And so the guy that had the computer in front that was controlling the car would, what happened? Would display, would target that speed. Let me go back to where we were here, because I want to point out a few things now in the upper part. And so it was telling the computer now target that speed. Okay? This is 6.5 meters per second, 7.5. You see that when we aim too high, we recreate some oscillation. Okay? But look at the numbers here that were the important ones. Fuel consumption. Let me point out, fuel consumption was not estimated. We had on every car OBD2 sensor, so it's the true fuel consumption measured on the car. Look what happens. When is regular traffic, there was around 19 liters used per 100 kilometers. Now, in the United States, you see everywhere miles per gallon. That's a non-linear measure with respect to the gallon, so it's usually confusing. Much better to use liters per 100 kilometers. That is a linear relation. So this is 19. When the waves were active in this phase of the experiment, we went all the way to 24.6 liters per 100 kilometers. And our best result of autonomy, we went down to 14.1. So we were making every car in the group, not only the autonomous group car, spare 40% of fuel with respect to the wave situation. So that's a big gain. The other big result here is the following. This is strong braking events. Means when your car decreased of more than 1 meter per second over a span less than a second. Is a very energetic braking. Okay, meter per second is not typically the measure you use it, but let me tell you, it's a really big braking. You are on the highway and you slam on the brake. So you see, when the waves were there, we had even above 8.5 events per vehicle per kilometer. So every single vehicle was slamming on the brake more than 8 times every kilometer. That, as you know, is around half of a mile. And you see, in our best situation, we almost erased that. They went down to 0.12. So one big break in every 10 kilometers, so much less. And obviously, if you decrease this big break-in, you increase a lot of safety.
So how many cars did you, were on the circle there?
Very good question. So these are exactly 21 cars. So that's another very important point, because we wanted to prove that we can control traffic with a small number of autonomous vehicles. What does it mean? Usually the technical term is penetration. That means what is the percentage of autonomous vehicle that, for instance, you can control with algorithm over the overall traffic. In this case, it is around 5%. We are controlling 5% of the car. In this case, means one car out of 21. That's a very important.
Very infinite long streets.
Yeah, and we will see. So this was obviously the toy experiment that was mimicking the Japanese situation. And then maybe let me recall what was the plan. Here in 2016, every one of these experiments is a nightmare, let me tell you. I mean, usually we were working an average of 16 to 18 hours a day to make this experiment, because there are so many headaches, complications.
Is that even legal? To work?
I'm not going to answer.
Don't racist.
You know, we are recorded, so you know I will not declare anything about that. So,
I mean, not in Europe, maybe the US.
yeah, I can tell you that everyone was safe. I will not say anything else. But you see, what Helmut was asking, the infinite stretch of road. So first of all, here we tested another thing. We were not testing our control, but we asked ourselves, okay, now the technology we are using is essentially automatic cruise control. Do currently commercially available automatic cruise control already do the job? Because then we have to do nothing, already commercialization. This was the proof that they don't. So this is a platoon. The first vehicle is the opposite of this. The first is human driven, the other have all ACC engaged. And you see the first human makes a little change in speed. And then as you go down along the platoon, this dip in speed goes down, 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 up to the last one that is so severe that disengage the ACC. So back then in 2018, the ACC were less evolved. And so when you would drop much lower than the speed that you set, it would disengage and it would go back to human control. So you see, back then it would disengage. So when you have enough cars, it would disengage. So it doesn't do that. I mean, in the traffic literature is called string stability. So it was not enforcing string stability. That means like taming oscillation, but it was rather increasing oscillation. So the bigger 100 vehicle test, in this case, not only we have a stretch of road, but we are immersed in real traffic. And we had 100 vehicles over a road where 150,000 people travel every day. So let me show you what happened. Again, everyone was safe. So first of all, how do you measure the impact of your experiment? There we equipped every car with a specific sensor to measure fuel consumption. How do you do an open road where you just control 100 vehicles out of 150,000? Well, what do? Well, you install a huge system made of cameras. This is a collaboration between Vanderbilt and the Tennessee Department of Transportation. This is a little clip of when they mounted all the poles. On every post, there were 6 high definition cameras. You may see here all the poles mounted there. And here is a picture you see of the pole and the camera watching over the traffic. These poles are 110 feet high. So, you know, they're big guys. The whole cost $11 million. This monitoring system was not used only for our experiment, obviously. It was done by Tennessee Department of Transportation for many reasons. But we were able to cover a stretch of highway of around 4 miles with the 300 cameras. And so, and interesting enough, the system was essentially completed between October and September of 2022. And we rushed to do the experiment in November 2022. And we did it in the second week of November. So essentially the system was ready in October, say. And we in mid-October, and we chose the second week of November to run the experiments. You know why? Any clue?
Thanksgiving weekend?
But that was one thing to avoid, because you need to avoid Veterans Day, other holidays, because the traffic is very different. People will tell you, oh, you did something else. So there is a daylight saving time change. And so you had much more light in the morning in the second week of November opposed to the first week of November. So that was the magic moment where to run the experiment, because the system was up and running and we had enough light in the morning. But that was really the best week to do that. So what happens is that, just an idea of the size of the system, there is a very famous data set dating back to 2006 called NGSIM with a 1,800 miles vehicle. An experiment in Germany using drones, 2018, 25,000. Our system with 300 camera continuously ongoing, here you see a little clips, records around 200 million miles run by vehicle per year. So you see, we're 4 orders of magnitude bigger than anything else was done in the world before. A little bit again of data from the experiment. There were, as I told you, these 1,410 feet poles to around 300 cameras. November 14, 18, morning rush hour, 100 cars we used, 97 in a row. They were indeed 100, 2 Toyota, 1 Cadillac, more than 7 researchers and some in physical presence, some remote, more than 170 drivers indeed, more than 30 support staff, around 300 people. This is a picture of the parking lot, and I will show you a little clip from which the cars were leaving. They were divided in 2 groups, an orange one, and you will see people dressed in orange vest that would drive on a certain route, and the yellow one that would drive on another route. And the blue vests were the researchers. So you see here, so you see some blue, controlling all the movement, keeping everyone safe and so on. This is the conference on the Friday where we were all happy that no accident happened, and the show of the 300 camera, and then work at the PI is a former co-advisee that was the PI of the I-24 motion system. This was my group there with various students and postdocs. Now, fortunately, a few of them have positions Canada, Amherst College, Berkeley, Paris, and so on. And this is the monitoring system. Obviously, we were watching all the cameras to check that, we were keeping safe. And this is a clip. You will see the orange people driving the car, the yellow one, and the blue vest. This is obviously a time lapse, so we were not so fast. And so you see the orange people are coming and going, the blue are controlling everything inside, then a yellow group would come, or another orange one would go. It was very cool. I didn't know in Tennessee could be so cool then. And what happened is that every driver was instructed, so they would receive a key, go get the car, receive various instructions, then they would drive, bring the car human-driven to the highway, then they would reach an assigned lane, and then when they reach the assigned lane, they would press the ACC button. But instead of the stock ACC, the car would use an algorithm that we put in the car, essentially hacking the car, so that the ACC button would correspond to our algorithm. Even more than that, we could push remotely the algorithm, and this was the monitoring system. You see all the cars distributed on the highway, different colors depend if they are hacking or not, and depending on the speed with which they were running. So they were pressing ACC like if they were normally driving and press that, but indeed our algorithm was inserted there. Again, we could push the algorithm even remotely. So we could change the algorithm during the experiment and so on and so forth. Usually we were fixing one algorithm per day, but we did even experiment in which we were using different fleets. So some car we were pushing one algorithm, some car we were pushing another one to test, our capability. To conclude, maybe a little bit about the control and results. We didn't publish any results yet. All the papers are written and so on, so I cannot talk, too explicitly about the results and so on. But this is the architecture of the control algorithm. So we had an external source of data traffic. There are fixed sensors that were transmitting data like density and speed that were feeding on a first software module called Speed Planner. The Speed Planner was essentially using that information when available to suggest what was the speed that our algorithm would track. And then there was a lower level algorithm that was interconnected with the electronic of the cars, in particular the CAN and GPS system, and would push essentially 2 different algorithms, because we had some cars in which we could access the data that the car was measuring, like distance from the car in front and so on. Some other in which we couldn't access all of that. So we had to design different battery of algorithms that were addressing the different cases. And these algorithms in turn were breaking in few pieces. Some pieces that would high level try to do the same thing that we did in the ring road. So try to drive in a different way so that to stabilize the system. But then we had other two modules that would take care safety first, whatever happens, be ready to stop. And then another one, because, I thought that the worst traffic I saw was in Rome when I was living there, back in 2008. But believe me, also on the I-24 in Tennessee, there are so many people do cutscene that we had to design on purpose another module of the algorithm that would take care when people were just making a very abrupt cutscene. All these together were able to control the vehicle, and this type of result at scale are like that. If you look at the map of data points of velocity and acceleration when no AV is present, you see that essentially they distribute like that. When the AV were present, these are the data points that we see. You see that it doesn't seem that much, but it reduces a lot the acceleration oscillation depending on the velocity, and this in turns transfer in estimates on the fuel consumption. Obviously, as I told you, in this case, we couldn't measure the fuel consumption directly, and so we had to resort to all the images, elaborating all the trajectory, and then estimated all the fuel consumption based on that. This is the end of my talk. Let me just thank, obviously, all the people that collaborated in my group. And as I told you, the whole group has 300 people, so much bigger. These are people in my lab, and obviously the founder, NSF, Department of Energy, and Department of Transportation. These are other funders that fund biology-related research I didn't talk about. Thank you very much.
Questions?
So in this circular thing, there's some speed about 7.5 meters per second where the control stopped working, right?
No, it's not going to.
Or it's reduced.
So let me try, maybe I was not clear enough. So our control tries to erase these waves, like to dissipate. And at the same time, targets a given speed. So it's like wants to dissipate the wave and travel at a certain speed. So we were telling the car which speed to target. And you are right, when we were staying below 7.5, it was able to dissipate waves. When we were going above, it was targeted the speed, but being less efficient in dissipating the waves.
So I'm wondering if there's a way how you could guess at this number 7.5, whatever the threshold was in terms of other things.
Absolutely great question. So let me tell you that during that experiment, it was a little bit of sweet spot. So, we tried, and that was what is. There are some estimates you can make by the number of vehicle on the road, on the ring road. And so it's a kind of computation of what is the density of that of cars. And then there are natural ways of associating expected speed. When you're on the open highway, you can still do that, but it's a bit more complicated because there are different drivers. As Helmut was saying, is a straight stretch of road, is not a ring, so the density is varying a lot. So usually there, we replace that sweet spot by outside information with either the speed planner, the upper part of the control, so using information from downstream traffic, or when that information is not available, we do something that is very similar to what the old TCP/IP algorithm was doing for internet traffic. That is, you start computing your ideal speed, you start a little bit lower, and then you start by increasing by small increase. And if you don't see oscillation, you continue to increase. If you see oscillation, you stop. That was the final way of addressing that. But in the ring road was, by attempt.
How powerful a computer did you need actually centrally to run?
PC.
Oh, APC?
Yeah. No, not at all. You see, after all, the algorithms are designed with this information about traffic down the road and local information about your own speed, the speed of the car, the distance to the car in front, and possibly the speed of the car in front, nothing else. So very, very simple. Yeah, simple algorithm.
So if you make a bigger circuits with more cars in and one is controlled, does it break down then? Because
such a-
all the wonderful.
I shouldn't be surprised that you guys are obviously getting all the main points. So it's so interesting that when you set the number of cars to infinity and keep just one vehicle, interesting enough, you can still stabilize. But the basin of attraction, you can decide, you can have two problems. You assume that the perturbation occurs, you try to stabilize, or you want to just keep stability. So the basin of attraction on which you can stabilize goes to zero, as you can expect. So, and also the time in which you stabilize. If there are 100 cars, your effect will take a lot of time before reaching the 50 cars. And so you can still stabilize, but the type of perturbation, the size of perturbation you can dissipate, and the time for dissipation both explode. But in principle, you can still stabilize with any number.
So it would be an investment to have a few cars on the highways
Oh,
to do
maybe
this.
I should go back.
Economical investment.
Well, I should go back to the question about the penetration rate. It was 1 car out of 10. Here, the penetration rate that we had to adjust, we didn't know what it's going to be because we cannot predict how many cars were there, but we were able to estimate between 1.5 and 3. And in reality, we kept around that range. And it's known that below 2% is very hard to do anything. So you need to reach a 2%. There is an ongoing experiment in California, in the Delville area, in which my California colleagues are recruiting people to exactly do that, to act as controlling in traffic. But they started this year, so I don't think they have a result to show yet. But that's exactly, it's a kind of crowdsourcing traffic control. Yes.
You might have said it already, but I heard that in some places, the municipalities are working on controlling, trying to activate in a smart way the traffic lights to avoid to reduce congestion. Does your algorithm integrate with that kind of efforts?
Very interesting question. So all the traffic regulation by traffic light problem is obviously a very well-established problem that started to be studied, shortly after the 30s, right? So I'm not an expert of that one. And you see, it's a very different control mechanism. So the control mechanism by fixed sensor or fixed actuators are like traffic lights. You control just a certain point of the network, right? More modern control could be traffic information, for instance. More and more you see those appearing.
But you have the mathematics of the stop and go mechanism, which also affects.
Yeah, not only that, but these type of controls are completely different. They are called Lagrangian control or probe controls because you don't have controls at a fixed position, but rather you have agents that are spread in the network and they actuate control all over the place. In general, the only comment I can say is the following. It's obviously easier to control in the Lagrangian sense phenomenon like waves because you have much more points where you can try to control. While the fixed sensor control is more difficult because you can imagine you control just a traffic light, then whatever happens upstream is very hard to control. So it's definitely that is a research area in which recently they used even AI and other stuff. So they're trying to address a lot, but it's really the conception of the control mechanism. That's the traditional control. This one is Lagrangian or new type of control, distributed control, if you want.
Okay, if there are no more questions, thanks. Yeah.